Good evening.
Good evening, sir.
Good evening, all the students.
Good evening, sir.
Good evening. Good evening, Jashri.
Good evening, sir.
Good evening. So today we will be starting with solid state physics part, small part of your syllabus. So first of all, we will study about crystal structure. So what are the types of crystal structure you know about?
Amorphous crystalline.
Yes, very good. So one is crystalline state. And what do we have in crystalline state? Regular or periodic arrangement. There is a regular or periodic arrangement of atoms or molecules. Okay. And why most of the solids they crystallize into crystalline state? Why it is so? Welcome, Durga. Good evening. Why most of the solids that we come across, they are crystalline in nature, they are not amorphous. Amorphous means that arrangement is missing. Regular arrangement is not there, it is random. But why most of the solids they tend to have regular arrangement?
So since they are tightly packed, since the atoms are tightly packed,
It means in amorphous solids they are not tightly packed.
so it means they're trying to arrange themselves in a very regular way and to give a better configuration.
But that is the question itself. Now, why they are doing like that? Of course, both are the solids. Now. So you cannot comment like that they are densely packed, they are less densely packed. So just by looking at the solid, we cannot judge. Isn't it?
Yes, sir.
Yeah, actually both are rigid. It's not like that one is solid and other is liquid, or one is not rigid, other is rigid. Of course, both are rigid. Amorphous solids. We are saying solids now, we are not saying liquids or gases. No, Arun, again you are wrong. How do you get to know about strong intermolecular forces? Basic, just think about the basic. I'm saying one structure is more stable as compared to other. What may be the reason behind? Yes, Yani, very good. Now, we study all the time that a structure having least energy is most stable. So that is the reason behind it. These crystalline states, they have less energy as compared to the amorphous state. That's why these are more stable as compared to the amorphous states. And that is the reason why most of the solids, they crystallize into crystalline states. Okay. So most of the solids. Can I write crystalline state is a low energy state and is therefore more stable or more preferred one as compared to amorphous state? In fact, this is the reason it is more preferred. Okay, that is the reason. Clear? Now, the crystalline solids, they can be further classified, maybe subdivided into two further categories: single crystals and polycrystals or polycrystalline. Solids, single crystal and polycrystalline solids. Now, single crystal means same kind of arrangement it is getting repeated up to infinity. Means we say that as a long range order. So there is a long range order of atoms. But in polycrystallines, there are small regions having different arrangement of atoms. Of course, arrangement is there, but that is not extended to infinity. So that arrangement it is limited to a certain distance. Then some other kind of arrangement is that. That's why polycrystalline. Poly means many crystals. Okay, clear? Is it clear?
Yes, sir. Yes, sir.
Now, next, in single crystals, the periodicity of atoms exhibit. Yeah, in other words, you can write extend. That is the more appropriate one. Extends throughout the material. Okay, whereas a polycrystalline material is an aggregate of a number of small crystallites with random orientation, separated by well-defined boundaries are there. And then one more thing, the small crystallites, those small regions are called grains. And the boundary there's grain boundaries. Clear?
Yes, sir.
So this was about the crystalline state. Now amorphous means completely random order. Order is completely missing, not up to a short distance even. Everything is completely random. Just like the students when the teacher is not there in the class. Okay, everyone likes to do whatever he or she prefers in the absence of teacher, or just as the students they play in the playground. Someone is playing cricket, someone is playing football, and others. Completely random phenomena. But once the teacher enters the class, everything is completely in order, just like the crystalline state. Okay, so that's how you can remember.
Yes, sir.
The non-crystalline or amorphous solids are characterized by the completely random arrangement of atoms or molecules. Like this. Clear? So glass is an example of amorphous material that we come across in our daily life. Glass. Okay. Noted?
Sir, glass comes under the category of solids or liquids because glass we call it as highly viscous liquid. So is it coming like solid or we still consider it in liquid?
Yeah, definitely we consider it as solid. Solid form. That window glass I'm talking about. That is amorphous. And this is the question asked in interviews also. That give the example of the amorphous material around you. Okay. Noted, beta?
Yes, sir.
Yes, sir.
Now, so what do you mean by crystal? So we have studied about crystalline state and amorphous state, but what do we mean by crystal? Please tell me. Anyone? Definition of crystal? Crystal is made up of two things: lattice plus basis. Basis is also called motif. You may find this word in some of the books. Basis plus lattice plus motif or basis. Yeah, which have regular arrangement, but so these two things are required. Now, why these two things are required? See, lattice means the empty structure. So it will tell us where to repeat. Basis means what to repeat. That's how you can remember. Means lattice is the empty structure devoid of atoms or molecules. Only empty structure is there. And basis means atom or group of atoms that you have to associate with each of the lattice point. So that's why I have written basis means what to repeat and lattice means where to repeat. So whenever we have combination of these two things, we get the crystal structure. Okay? Clear?
Yes, sir.
It means lattice means it is an empty structure. Lattice means it is simply an empty structure. And basis means atom or group of atoms. Okay? You may be repeating the atom or a number of atoms. And that's how you can get the crystal structure. Definition clear to all? So with the help of these two words, we have made the definition very simple. Where to repeat, what to repeat. And now lattice is also called space lattice. Okay, a lattice is also called space lattice, or even previous lattice in some contexts that we are going to study later. And what do you mean by lattice? Now it means lattice is an array of simple points because it is not having atoms. So if we have to define the lattice, how we can define it? It is an array of, array means structure, simple, array of points in space such that every point has identical surroundings. Only then it will be regular arrangement now, when the surroundings are identical. Clear? Is it clear or not?
Yes, sir. Clear.
So I'm giving you the very simple definitions, simple and smart ones, which are easier for you to remember, not the usual bookish language. Okay. Now there may be 1D, 2D, or 3D lattices. but there are some kinds of symmetries prevailing in the solids. Now, depending upon those symmetries, we are able to restrict the number of lattices to a particular number. Okay, is it clear what I'm talking about? There are certain symmetries. What are those symmetries? They may be reflection symmetry, they may be translation symmetry, there may be rotational symmetries. So many symmetries are there. Na? Of course, we will study about the rotational symmetry later on. So looking at these symmetry operations, we are able to restrict the number of Bredis lattices in 2D and 3D to a particular number. Okay, clear? Is it clear or not?
Yes, sir.
Okay.
Yes, sir.
Now, let us discuss something about the translational vectors. Okay. So we have already studied about the space lattice. Now, space lattice. Now, we said that each of the point in the lattice, it is having the identical surroundings. Identical surroundings means same kind of appearance is there. Okay. Now, let me make one particular diagram, and then we will discuss. Don't make the diagram right now. Let me complete. Okay. This. So what I have done is I have considered two vectors, v1, v2, a1. Okay, so I have chosen two vectors. Now I can write any translational vector. This is translational vector in the form. This is for a 3D, but I have taken the example of 2D, of course, because it is easier to visualize in 2D. Right now I'm writing the equation for 3D. It is like this, and where A, B, C are the primitive vectors. Usually we say, this is, you can write translation operation. Means if I have to migrate from one lattice point to another point, then the help of the translation operator or the translation vector it is taken. Okay. Means if I have to move from one point to another point like this, then this is done with the help of T vector. Okay, it's like this. And here n1, n2, n3 are the integers. And the vectors A, B, and C are the fundamental translation vectors. Now, as I said, we can obtain a new point from old point by using this P operator. So this will be the relation between the old point and the new point. Please check. Let this be 1 and this be 2. Okay. Clear?
Yes,
Sir, what is R vector dash?
Yeah, this is the new vector from the old vector. Wait for that, I'm telling you.
Sir, what is the requirement of the atoms to extend their position from one lattice to another?
Lattice is only the empty structure, but the solids, they are made up of atoms. So we are associating the crystal structure with the solid structure, with the atoms. Every solid, just as we discussed earlier, that most of the solids, they crystallize into crystal structure. So actually, we are trying to study the structure of those solids. That's why we are associating the lattice with atoms also. Otherwise, only lattice would have been sufficient. Okay?
Okay, sir.
Lattice means free from atoms. It is the only geometrical structure. But whenever you place the atom, only then you get the crystal. Because I said crystal is lattice plus basis.
Yes, but if मतलब कभी अगर एक जगह लैटिस का फिल हो गया एटम के द्वारा तो उसके बाद उसका ट्रांसफर क्यों हो रहा है दूसरे लैटिस में?
I'm not getting your question. Lattice तो एक ही होगा ना बेटा, दो lattice कहाँ से आए?
नहीं, एक क्रिस्टल में लैटिस कितने होंगे सर?
एक crystal. What do you mean by crystal? First of all, tell me. Crystal means lattice plus basis, na? And crystal is solid, na?
Yes.
Crystal means solid, and solid is having a definite shape, na? So there will be only one and one lattice for a particular crystal, na?
Okay, sir.
It is not changing its shape, beta. So it is having a definite shape. It means you can associate one lattice with one crystal. That's it.
Okay, sir. Got it.
Only one crystal is
Okay,
there.
sir.
Only one lattice is there. Actually, what we are studying is within that lattice. Now, lattice is there. So lattice is a big structure, na? So lattice is having a number of points. Suppose 10, 20 points are there within a particular lattice. And on those points, you have to place the atoms. Just forget about it that you are placing the atom. But lattice is having number of points. Now, if I have to move from one point to another point, then what is the method? What is the way? That is done with the help of P vector. That's what we are studying. Means suppose this is a lattice. I have to move from this point to this point. I have to move from this point to this point. Okay? That's what we are doing. We are not changing the lattice. We are changing the lattice point.
Okay, sir.
Now, this relation 2, it will be obeyed for a perfect lattice. For a perfect lattice, this relation is definitely obeyed. Equation number 2. But for imperfect lattice, this is not obeyed. Okay, so for a perfect lattice, equation 2 is obeyed or applicable. However, in an imperfect lattice, it is not possible to find ABC such that equation 2 is valid or obeyed. Means this is not possible in imperfect. Imperfect word itself means the lattice is not proper, not perfect. No? It means for some of the lattice points, this equation will not be obeyed. Okay?
Yes, sir.
Clear?
Yes, sir.
So I have shown two such possibilities in the diagram. Let's take it A2 also. So what I have done is I have taken two possibilities of such vectors for 2D. One set I have taken as A1, B1. One such set. Okay? One such set has been taken as A1, B1. And another such set, it has been taken as A2, B2. Please check. Actually, what is there? Let me tell you. Okay, I will make it on the next slide again to give you a better idea. What is this? Okay. Note it.
Sir, which lattices are called perfect lattices and which one are imperfect?
In which this equation is obeyed, those are perfect. Those in which this equation is not obeyed, those are imperfect.
No, not mathematically, but like in terms of structure or something like that.
It means structure will not be extended to infinity. Long range order will not be there. No? Some of that will be. And you keep yourself muted. Now they are here. What are you doing? Please, beta, keep yourself muted. Yes. See, if I displace some of the atoms or some of the points from their normal position, okay, then it might be possible that in order to go from one point to another, this equation may not be obeyed. No? Actually, there are lots of imperfections in the crystal. Imperfection means the crystal is not in its proper state. It may be due to various reasons. It may be due to temperature. Some of the atoms within the crystal, they may be displaced from their original position, or sometimes due to the presence of impurities. The atoms, they are not at their regular positions, so and so. You might have heard about the word short defects, short-eye defects, etc., etc. Okay, so lots of crystal defects and imperfections are there. So because of that lattice, they are imperfect. So if I say, then none of the lattices, they are perfect, because ideal koi cheez nahi hoti beta. Nothing is ideal. Na? So the only thing we can say is that they are 99% perfect. We can never say that they are 100% perfect. Okay? Clear?
Yes, sir.
Now, let me tell you why I have made these two vectors or how they comes. Actually, there is a 2D arrangement of atoms, 2D, like this. Now you will get the better idea that why do we require this P vector or A vector, B vector, what are those vectors, what is the relevance. So what I'm drawing, can anyone tell me?
Lattice.
Yes, lattice, very good. So I have made a 2D lattice for you, a 2D lattice. Okay. So now we can make vectors like those I made earlier. Na? See, this was A1 in the earlier diagram. Now please check. It means in order to go from this atom to this atom, this vector is required, na? Or not? A1 vector is required, na? And similarly, in order to move from O to new position, this B1 is also required. Na? Please check. Are they required or not?
Yes, sir. Required.
Required. Na? So it means P vector, it will consist of A1 and B1 vector. And another possibilities. Let me tell you about another possibility. You could have gone for this one also. Na? Actually, I have made the diagram random. Na? That's why some of the lines, they are not proper. Like this. We could have chosen this one also. Na? Now clear or not? And that A2 is similar to earlier one, but B2 is different from B1. Even now I am able to translate one position to another, isn't it? Please tell me.
Yes, sir.
Now suppose this is point R. Let us suppose this is R and this is R dash. Now in order to move, there was one more atom. Okay. Now in order to move from R to R dash, what has to be done? You want to go from R to R dash position, and you have to make it possible with the help of A1, B1. Is it possible? Yes, anyone?
Sir, the B1 vector we can shift it to that line.
Yeah.
R.
What will be the relation? What will be the relation? R1 vector, R plus B1 vector. Can I write it?
Yes, sir.
If I write them in vector form, mean R1 vector will be this vector, na? This one. This is R vector, this is B1 vector, triangle law. Clear or not? And at this place, can I write 1 times B1? Or can I write this as R vector plus 0 A1 plus 1 B1? Is it?
Yes, sir.
It means in this case, T vector is 0 A1 plus 1 B1. And you can see these are integers, na? N1 and 2. because we asserted that these n1 and 2 should be integers. Okay, it means with the help of a1 and b1, I was able to get r dash from r. Now let us try the same thing with the help of a2 b2. Now please tell me, what can be done with the help of a2 b2 if you want to get that r dash vector? Please.
Sir, R2 R dash, that it is perpendicular to both OR and O that B2. So is it cross product or something like that?
No. You have to add, na? What was the relation? It is r plus t. How you can think about the cross product? See, these atoms, they are lying midway between these atoms. Na?
2B2.
So it means it will be half of a2, na? This much distance. And similarly, this distance also is half of this distance. This much distance. Suppose I'm joining this to this. Then this is lying midway. Na? So this distance is equal to this one. Na? So can I write it as half b2? Please check. You are moving half a2 towards right and then half b2 in the upward direction in order to reach r dash from r. Isn't it? This is the diagram. Na? First you are moving half a2 towards right and then half b2 vertically upward. Or you can do the reverse also. First you can move upward and then towards right. Okay? Clear or not?
Yes.
Yes, sir.
So why we took one B1 vector there?
Where beta? Earlier.
Yes, sir.
You have to go from r to r dash. Which vector you will add? A1 or B1? Have a look at the diagram. When you are going from this point to this point, which vector is to be added? B1 vector, no? It clearly shows that the vector connecting r and r dash is B1. So that's why I have written one B1, because there was nothing in front of B1, so we can associate 1 over there. No? And A1 was missing, that's why I have written it as 0 A1.
Yes, sir.
It means the translation vector is like 0 A1 plus 1 B1. But here you can see, I'm not able to get the integer values of N1 and N2. So are these A2, B2 vectors possible then?
No, sir.
No.
Of course, these are, but we will not prefer them. It means you might have read the term primitive vectors, primitive translational vectors. Have you read about that?
Yes.
So whenever you are able to get N1 and N2 as integers, those vectors they are called primitive translational vectors. So this set A1 B1, this set of A1 B1, it is called primitive translation vectors because they are associated with integer values of N1 and N2. But this set half A2, half B, because you are getting half now, these are called non-primitive translational vectors. So is it clear or not?
Yes, sir.
Means A2 B2. A2 B2, they are called non-primitive translational vectors. A1 B1, they are called primitive translational vectors. These non-primitive means A2 B2. It means A1 B1 will be more preferred as compared to A2 B2. Okay? Clear?
Yes, sir.
Why primitive one more preferred? Because they are associated with the periodicity of the lattice or the crystal. They clearly reflects the periodicity of the crystal. And usually, what are the primitive ones? Those having the shortest ones. Shortest possible vectors. Of course, A1, B1, they were the shortest as compared to, because B2 was longer in the second case. Of course, A2 was similar as A1. So the vectors having the shortest possible length, if they can be associated, they are always the primitive ones. Clear?
Yes, sir.
Any doubt to anyone?
So actually, I have a doubt in first equation that r dash vector is equal to r vector plus 1 b1 vector. Sir, according to the triangular law, it could be like r plus r dash vector is equal to b1 vector.
How you can say that?
Because
Have you seen the directions of r and r dash vector? According to me, I cannot add r vector plus r dash vector because in order to add the vectors, r vector should be in this direction. Only then you can add them up. The second vector should start where the first vector ends. Only then they can be added. But this is not the situation over here. R and r dash, they are starting from O.
Okay, sir, it was like that.
Here the situation is this. R is ending over here, and then there is B1. So only there some can be represented by r dash, according to triangle law. So that's why I have written r dash as r vector plus 1b vector. Okay?
Yes, sir. Sir, actually, I was confused about they are starting from origin or not.
Yeah, obviously that is the reference point because I'm taking all the vectors from O only. Na? You can see in the diagram A1, A2, B1, B2 all have been taken from O. Okay. So now it means with the help of this translational operator, which was made using the primitive translational vectors, of course, I can shift from one lattice position to another. Okay? It means we can do that. It means there are translational operations possible within the crystal. And because of the periodicity of the crystals, these are called translational symmetric operations. Some. Okay? Now similarly, there are rotational symmetries also. When we rotate the crystals with respect to some angles, we will end up getting the same kind of crystal as it was earlier, before rotation. Just as you rotate the sphere, you are not able to judge the difference. Na? If you rotate the sphere around any axis by any angle, you are not able to judge the difference between the rotated position and initial position, na? Because sphere is symmetrical. Similarly, if we rotate the crystal by some particular angles, not by all angles, then we cannot judge the difference between the new position and initial position or the old position. Those are called rotational symmetric operations. Okay, clear?
Yes, sir.
So
Yes, sir.
based on the symmetry, these and there are reflection symmetric operations also. Okay, so based on the symmetry, we are able to restrict the previous lattices to a particular number. Okay. So, but first of all, what do you mean by unit cell? Before discussing about the previous lattices, you should know about the unit cell. Please tell me.
So the collection of all points in the lattice.
No.
The smallest structural unit.
Yes, smallest structural unit. So whenever we say structural unit means just like the brick while making the home. So bricks, they are getting placed at the different positions. So that is the structural unit. So similarly, in case of crystal, smallest unit, which is when repeated in the three-dimensional space, that will provide you the crystal structure. That is called unit cell. Okay. And how many types are there for the unit cell? These are of two types. And what are those? Primitive
And non-primitive.
and non-primitive. So what is the difference between primitive and non-primitive? Those which are having one atom per unit cell, they are the primitive ones. Or having atoms at corners only. This is also the definition. Having more than one atom per unit cell. Those are called non-primitive. Okay. Clear?
Yes, sir.
Now, let us talk about rotational symmetry and then about the crystal structure and various lattices. Rotational symmetry. Now, for that, we suppose this is the top layer of atoms and this is the bottom layer of atoms. Okay. And these are the atoms. For example, this was the atom, this was the atom, this was the atom, and this was the atom. And of course, this is also the atom just above this one. And there is also an atom above this one. And then we have rotated the crystal, and then this atom, it gets shifted to this position. Okay. And similarly, this one at this position. And let us assume this angle is phi. So then this one is also phi. So this one is also phi, alternate angles. And let us assume that the lattice constant is A. Lattice constant means the distance between the neighboring atoms. Okay. Distance between the neighboring atoms. Clear? Is it clear or not?
Yes, sir. Clear.
So it means this is also A, na? Because this is the rotated position of this one. Or you can number these PQ, RS. This is PU, and this as AAB. Okay. So PA is rotated position of PT. Na? So the length will remain same, na? Because PT is A, so PA will also be equal to A. And because QU is A, so QP will also be equal to A. Okay. So can you get me the values of AR and SB? What is AR? In right angle triangle, ARP. We have to find AR and we know AP. So AR by AP is cos phi. Na? So AP is A. So AR is A cos phi. Similarly, because the structure is symmetrical, if AR is A cos phi, SB is also A cos phi. Isn't it? Now, A and B are the positions of the atoms. Can I break this AR into three parts like this? Please check.
Yes, sir.
Now, because we have assumed that the lattice constant is A, so the distance between any two atoms within the crystal, it should be integer multiple of A. Na? It cannot be having half integer multiple, na? Because then the lattice constant would be A by 2 rather than A. When you are saying that lattice constant is A, it means distance between any two atoms, it should be integer multiple of A. Na? Isn't it? Please tell me.
Yes, sir.
Is this clear to you?
Yes, sir.
Because if the distance between the atoms, it is less than A, then A cannot be the lattice constant. Na? So when the distance between any two atoms, any two neighboring atoms is A, it means the distance between any two atoms, it will be integer multiple of A. It cannot be anything else. So it means, can I write this AB as equal to M times A? Can I do so? Where M is integer, because it should be integer multiple of A. Na? Please check. Because A and B are the positions of the atoms. Na? So the distance between them should be equal to M times A. Clear?
Yes, sir.
So now can we find the possible values of M by solving this equation?
Sir, how exactly it is rotated? Because it's pretty confusing. Like it is rotated in the backward direction, like AS is rotated in the backward direction, or like how is it rotated?
I clearly said that PT is rotated as PA. you are bringing this atom at this position after rotation.
So this phi angle is actually towards me, like facing towards me.
Towards me, what?
I mean, the TP is the T. It is brought to that A, so that phi angle is facing towards me, right?
Facing towards you. Yeah, of course, if you are sitting in front of me, then it is towards you. From my position towards your position, then.
And that BQU, that angle is at the back direction, like at the back of it.
No, not at the back of it. It is again same. From my position to your position. But it is anti-clockwise. That one was clockwise. That is the only difference.
Okay.
P and U, they are lying in the same plane, and A and B, they are lying in the same plane. So you are just rotating the atoms from the lower plane to upper plane. So you are just rotating them like this, from my position to your position, like this. Are you able to see?
Yes, sir.
So that's how those angles are fine. Because the phi will be calculated between the new position and old position, and PT was old position and TA is new position. It means you have rotated the crystal by angle phi.
Yes, sir.
It's like this, no? Okay.
Yes, sir.
So now, what are the possible values of phi that we have to see? That is the question actually. Now see how it comes. So 2a cos phi, it will be ma minus a. So can I take a common from right hand side? So cos phi will be m minus 1 by 2. Can I call this as equation number 1? Now cos phi is a bounded function. Bounded means it is having some minimum and maximum value. And it lies between -1 and +1.
Yes,
And
sir.
we have proved that cos phi is equal to m minus 1 by 2. It means m minus 1 by 2 will lie between -1 and 1. Clear? So multiply by 2. It will become -2 less than equal to m minus 1. Add 1. So it will become -1 less than equal to m less than equal to 3. So only these values of m are possible. Means only 5 values are possible. -1, 0, 1, 2, 3. Okay? Clear?
Yes, sir.
Now let us make a table. So in that table, the first line will, first row or the column will correspond to m, and then m minus 1, and then cos phi, and then fold. I will tell you what do I mean by fold. So m minus 1, and then cos phi, and from cos phi we can get phi, and then fold. Fold is m. It is calculated by dividing 360 by the angle. That is called fold. Fold means how many times I have to rotate to complete the angle 360 degree. That is called fold. Now what is the first value of m? -1, 0, 1, 2, 3. These are the values. No? If m is -1, what is m minus 1? -2. Cos phi is half of it. What is the value of phi then? Cos 180 is -1, so minus 2. Na? Please check. Now you can see, after 4 you are getting 6, so 5 is missing. Now after 6 we should get 7, but again that will be missing. Because 1 means either 0 degree or 360 degree. But of course we cannot divide by 0, so we will take it to be 360 degrees, so again 7 is missing. So that's why we always say that 5-fold and 7-fold rotational symmetry does not exist. Clear? And there is another way of interpreting these results. They can also be put in a different format. Actually, what we can do is, I can do the reverse of what we have done. If I start by the value of the fold, I can get the angle. Okay, if I start by taking n equal to 5, of course I can get the angle. And similarly for n equal to 7 also we can get the value of 5. So tell me those values of 5 that you get by taking n equal to 5 and 7. Please, for n equal to 5 you will get 72. And for n equal to 7, near about 52 you can say.
Yes, sir.
Approximate. Na? So this is the meaning. This is another way of interpreting it. It means the crystal will not, or the crystal environment will not look to be the identical to initial one if you rotate the crystal by an angle of 72 degree or 51.43 degree. Okay?
Yes, sir.
Clear to all?
Sir, what does that fold
sir.
means?
Fold means how many times you have to rotate to complete the angle 360.
Okay.
The number of times you have to rotate. If it is 180, it means you will be rotating the crystal by twice to get the 360 degree angle. That is what fold means. Clear?
Yes, sir.
Yes, sir.
Now, depending upon these operations, rotational symmetry, translational we have discussed, and there are reflection symmetries also, because there are various planes in the crystal in which if we see the reflection of the crystal structure, it will look to be the similar to earlier one. So based on these symmetry operations, there are now 2D lattices. So there are 4 crystal systems in 2D. 4 crystal systems. And what are their names? We can make the table: serial number, crystal system, and then Bravais lattice associated with it, and then conventional unit cell associated with the same, along with its parameters, of course. So oblique. This I'm talking about 2D only, okay? Unit cell is parallelogram. And of course, in parallelogram, angle, the sides are not equal, and angle is not 90. Rectangular. So 2 kinds of rectangular lattices are there: rectangular primitive and rectangular centered. So the unit cell will be rectangle, and again for rectangle A not equal to B, but angle is 90. And then it may be a square, and in square, you know, A is equal to B, and of course unit cell will also be a square. And last is it may be hexagonal. Four crystal system, but various lattices are 5. You can count because there are 2 rectangular lattices, rectangular primitive and rectangular center. Center means in which one atom is there at the center. Primitive means only atoms at the corners are there. So they can ask you about the number. Simple question: that how many various lattices are there in 2D? How many crystal systems are there? And of course, these relations between A, B, and gamma. These you have to remember. Okay? Clear?
Yes, sir.
Yes, sir.
Now 3D lattices. So this is much more important. Of course, 2D was also important. No, Arun. Actually, this is the angle between your base vectors. No? When you make a rectangle, what is the angle between the adjacent sides? So that angle we are referring to as gamma. Okay? Means you will be making some smaller unit. No? That is called conventional unit cell. So in that unit cell, what is the relation between the sides of that unit cell and what is the angle? Those are A, B, and gamma. So 7 crystal systems are there. And what are those? Number 1, cubic. In cubic, A equal to B equal to C. So I will tell you the way to remember these because it is very critical to remember otherwise. So I will give you a mnemonic also. Okay. And here there will be 3 angles. So all the angles are equal to 90 degrees. Now, if you can learn these names in order, na, tetragonal, and then orthorhombic. Now, what you can do is just go on reducing the symmetry. Means first make B not equal to C, then all the 3 not equal. Starting with all equal, then B not equal to C, then A not equal, B not equal to C. But then the names, they should be in order. But all the angles, they are 90 degrees in first 3. So 4 is trigonal, and another name of trigonal is rhombohedral. Now, again, you have to start with A equal to B equal to C after 3, and again, same procedure. Not equal to C, A not equal to B not equal to C, and in last also, A not equal, B not equal to C. So alpha, beta, 90, but not equal to gamma. And in hexagonal, alpha, beta, 90, of course, and gamma is 120. Here, alpha and gamma, they are 90, but beta is not 90. Here, none of the angle is 90. So, of course, it is easier regarding the sides, if you can remember this order. And for angles, you have to be a little bit careful. Not that difficult, but actually you can remember that in triclinic, nothing is equal. That's how you can eliminate that. And in first 3, alpha, beta, gamma, they all are equal. And for hexagonal, you can. And in hexagonal, alpha, beta is 90, and of course, one angle is going to be 120 because it is hexagon. Okay? So that's how you can remember most of the things. Now, what is the mnemonic? How to remember this order? Because otherwise, it is very difficult. Okay? So I have a mnemonic for you. So what you can do is, have you made this table?
Yes, sir.
Yes, sir.
Now, let me write the mnemonic here. Chemistry, comma, trigonometry, or history, may, top. So you have to take first alphabet of these, the capital ones, the ones that are represented by capital ones. First one is C. You can see here. C for cubic, T for tetragonal, O for orthorhombic, R for rhombohedral. Why not T? Because then you would be confused between tetragonal and trigonal. So I have represented trigonal by rhombohedral. Then H for hexagonal, M for monoclinic, T for triclinic. That's how you can remember this order. Clear? Is it clear?
Yes, sir.
Yes, sir.
Now one more is there.
Yes, sir.
One more is there with me. Another one. That is the short one. Cute. Or of course you can make your own mnemonics also. You are very smart. Okay, you can make your own mnemonics. So these two I have made. So C, cute or hot, mera trick. तो आप कुछ भी बना सकते हैं. There is nothing special about these tricks, but they will definitely help you. So C means cubic, T means tetragonal, and O means again orthorhombic, R means rhombohedral, H means hexagonal, M means monoclinic, T means triclinic. So whatever you feel convenient with. Okay, and of course you can make your own. Clear?
Yes, sir.
Now 14 Bravais lattices are there. Only 7 crystal system, but how Bravais lattices there are 14. So how many types each crystal system it is having? Now, first of all, let me write serial number, crystal system, and then types. Types are simple cubic, body centered, face centered, and end centered. And you keep yourself muted. So cubic. Then
So what is SC?
yes.
So what is SC?
Simple cubic. Simple cubic, body centered cubic, face centered cubic. Now okay. And end centered, that is easy. So second one is tetragonal, third one is orthorhombic, trigonal or rhombohedral. Hexagonal, monoclinic, and then triclinic. So in cubic system, simple cubic, body centered cubic, face centered cubic are there, but end centered is not there. So I'm putting the tick marks. It means in the end we have to count these tick marks. Okay. Now in orthorhombic all are there, and in trigonal only simple cubic is there, and in hexagonal also. And in monoclinic, simple cubic and end centered are there. And in triclinic, means simple cubic, it is always there. And rest of them you have to remember. Now you can count these tick marks, they will be 14 in number. So that's how 14 Bravais lattices are there. 7 crystal system and 14 lattices, types. Please check. Okay. Clear?
Yes, sir.
And one more information. Cubic state is the most ordered one, and triclinic is the least ordered one. As you can see from this table, that in case of cubic, all the sides and all the angles they are equal. But in triclinic, none of the sides and none of the angles they are equal. So let me write these states in the order of their symmetry. Okay. So crystal systems. In the order of symmetry. And of course, symmetry is increasing this way. So means the most symmetric one first and then. Okay, so cubic, then there will be hexagonal. So here you can write increasing symmetry. Cubic, hexagonal, then tetragonal, trigonal, orthorhombic, monoclinic, triclinic. Okay.
Yes, sir.
So cubic is the most symmetric. Okay. Clear?
Yes, sir.
Yes, sir.
So this was the basic about the crystal structure and Bravais lattices and all. Of course, there are questions from this part, that how many crystal systems are there and what is the relation between A, B, C, alpha, beta, gamma, etc. The one that based on rotational symmetry that we have discussed. Okay. And of course, they can ask you about a particular material, whether it is crystalline or amorphous. So tomorrow we will discuss about the various crystal structures cubic crystal structures. They are in our syllabus, and cubic means we are going to discuss simple cubic, body-centered cubic, and face-centered cubic. So everything about these structures, and of course the related questions then. Okay, so that's all for today, students. So we will meet tomorrow. Okay, bye bye. Take care.
Thank you.
Thank you, sir.
Thank you,
Thank you,
sir.
sir.
Thank you, sir. Thank you, sir.